Dear learners, I am Venkatakrishnan, Assistant Professor, Department of Mathematics, Ishwari College of Engineering. In this video, we will be discussing covariance of two random variables. We are already familiar with variance of a random variable. That is, it is the how far a value deviates, how far a random variable deviates from its mean is called the variance. And we know it is given by the formula for variance is E of x squared minus E of x the whole square, or in short we can say it is the average of x minus x bar the whole square. So a random variable, how far it varies from the mean of its mean. So this is called as variance. Now we'll be discussing the covariance. So how a two-dimensional random variable? A two-dimensional random variable is nothing but two different random variables defined on the same sample space. So how a two-dimensional random variable deviates from their respective means. That is how far x deviates from its mean, that is E of x, and how far y deviates from its mean, that is E of y. The symbol to denote the covariance is COV of x comma y, and it is given by expectation of x minus the average value of x, that is the expectation of x, into y minus the average value of y, that is expectation of y. So because because of its representation, it is also called as product moments of x and y. Now let us discuss the formula for covariance under various cases. Suppose we have in general, this is a formula that is on simplifying. That is, what we had is expectation of x minus E of x into y minus E of y. This is what we took as the formula for covariance. Now you just open up the brackets and apply the property of expectation. So it is E of xy minus x into E of y minus y into E of x plus E of x into E of y. Now applying the properties of expectation, we have E of xy minus E of x into E of y, because this E of y is a numerical constant and we know expectation of Ax is A into expectation of x. So again applying the same property, it's again E of x into E of y plus E of x into E of y, which can be simplified as the result we have taken here, E of xy minus E of x into E of y. Now suppose we are given the joint distribution of two random variables x and y, then how will you compute the covariance? What will be the equivalent definition? So the expectation of xy when the joint distribution is known, it is double summation xi yj into pij, and the expectation of x is nothing but xi into marginal probability distribution of x, and the expectation of y is sigma y into marginal distribution of y. Now this is the case of the continuous two-dimensional continuous random variables. Here the formula for expectation of xy is double integral over d, we can say the domain in which the x and y are defined, xy into the joint density f of x comma y, and we know in case of two-dimensional random variables expectation of x is integral over range of x into marginal density of x. Similarly expectation of y is y into marginal density of y. Instead, when the values of x and y are tabulated, we know the expectation of x is nothing but the weighted average. So it's nothing but the average. So take the product xy, compute the average. So sigma xy by n. Expectation of x is nothing but the arithmetic mean of x, that is the average value of x, sigma x by n, and the expectation of y is sigma y by n. So it is sigma x into sigma y by n squared. So this is the case when the values are tabulated. Now let us discuss two problems based on this covariance. The first one would be the problem based on two-dimensional discrete random variable. We are given the mass function of the random variable x and y, that is the joint probability distribution of x and y. Here x takes the value minus 1 0 1, y takes the value minus 1 0 1, and we know the tabular form of the joint distribution, that is when x is equal to 1 and y equal to 1, the probability is 1 by 6. The probability that x takes 0 and y takes minus 1 is 1 by 3, and we also know how to compute the marginal distribution of x and y. So based on this, now we are asked to show that their covariance is 0. Okay. Now let us find the covariance. Now we know E of xy is nothing but xi yj. So when x is minus 1, y is also minus 1, the probability it takes x minus 1 and y minus 1 is 1 by 6. So a minus 1 into 1 by 6, and now x into y, x is 0, so 0 into anything 0. Now if x takes 1 and y takes minus 1, it is 1 into minus 1 into the probability with which it takes this value is 1 by 6. And now here we have 0, y value 0 means x into 0, so the entire row it is going to be 0. So we move on to the third row, x takes minus 1 and y takes 1, and this happens with probability 1 by 6. So 1 into minus 1 into 1 by 6. Again we have x is equal to 0, so 0 and anything 0. Now we have x is equal to 1, y equal to 1, and this happens with the probability 1 by 6. So it is also 1 by 6. So now adding, we have plus 1 by 6, minus 1 by 6, minus 1 by 6, plus 1 by 6. So E of xy is 0. Now to compute the expectation of x and y, we need the marginal probability distribution of x and y. So when x is equal to minus 1, you vary y, keep x is equal to minus 1 and varying y, add those values 1 by 6 plus 0 plus 1 by 6, so it is 1 by 3. Now adding, when x is equal to 0, keep varying y and add those probabilities, so it is 1 by 3 plus 0, which is again 1 by 3. Now x is equal to 1, keep x is equal to 1, vary y, so add all those probabilities, 1 by 6 plus 0 plus 1 by 6, which is again 1 by 3. Now if you want the marginal distribution of y, take y is equal to 1, vary your x, add all those values, so 1 by 6 plus 1 by 6 plus 1 by 6, it is 2 by 3, here it is 0, and now when y is equal to 1, vary x, 1 by 6 plus 0 plus 1 by 6, it is equal to 1 by 3. So using these marginal distributions, now let us compute our expectation of x. So here we have tabulated the marginal distribution of x, and the expectation of x is, when x is minus 1, the corresponding probability is 1 by 3, and when x is 1, the corresponding probability is 1 by 3. So expectation of x is the sum of their products, it is 0, that is the weighted average. In similar fashion, the marginal distribution of y, what we have found out, we have tabulated here, and the expectation of y is the value of y into its corresponding probability, and sum, and their sum, it is minus 1 by 3. So now the formula for covariance, it is E of xy minus E of x into E of y. So we have the covariance to be 0. So the covariance of x and y is 0. This need not imply that the random variables are independent, because if you take p of x is equal to minus 1, y is equal to minus 1, from the tabular column the value is 1 by 6. But P of x is equal to minus 1 into P of y is equal to minus 1. It is equal to 1 by 3 into 2 by 3, that is equal to 2 by 9, which is not same as their joint probability. So we can say x and y are not independent, though their covariance is independent. X covariance is 0, x and y are not independent. But when x and y are independent, obviously their covariance will be 0. Now we shall have one more problem on continuous two-dimensional continuous random variables. So here we are given the joint density function of the two-dimensional random variable x and y. We are asked to compute the value of c and covariance of x comma y, and we all know how to compute the value of c. We can use the property of joint density function. That is, when we integrate the joint density function in the domain of the two-dimensional random variable, the value of the integral turns out to be 1. So here we can even plot the domain. So x varies from 0 to 2 and y varies from 0 to 2. So this is x is equal to 2 and the y axis x is equal to 0. Similarly, the x axis y equal to 0 and this is y equal to 2. So this is going to be the domain of the two-dimensional random variable. So now let's apply the property of the joint density to get the value of c. So integrating it over the domain 0 to 2, we get c is equal to 1 by 8. Now we proceed to compute the marginal density of fx, marginal density of x and marginal density of y. Now substituting back the value of c we have evaluated, we have found c is equal to 1 by 8. That you substitute in the given joint density function. So it is 1 by 8 into 4 minus x minus y. So now let us compute the marginal density of x, and we have already plotted the region. Now on taking the here we have to integrate the joint density, we have to integrate with respect to y. So taking the vertical strip, the limit we get 0 to 2. So integrating the joint density between the limits 0 to 2, we have the marginal density of x to be 1 by 4 into 3 minus x. Okay. Now similarly, let us compute the marginal density of y. So again it is the integral, we have to integrate the joint density with respect to x. So taking horizontal limits, again the limit is 0 to 2. So we get the joint density of y to be 1 by 4 into 3 minus y between the limits 0 to 2. Now let us compute the expectation of x. We know the expectation of x in case of two-dimensional random variable is integral over range of x into marginal density of x. So here the marginal density of x is 1 by 4 into 3 minus x. So substituting the marginal density and evaluating, we get the expectation of x to be 5 by 6. Similarly, expectation of y in case of two-dimensional random variable is the integral in the range of y into marginal density of y into dy. It should be dy. So on evaluating the integral, we get the expectation of y to be 5 by 6. Now let us compute the expectation of x, y. It is double integral over the domain of x and y, xy into the joint density function of xy. That is 1 by 8 into 4 minus x minus y, and evaluating the integral, we get expectation of xy is equal to 2 by 3. And now we have e of x, e of y and e of xy. So just apply in the formula for covariance, which is e of xy minus e of x into e of y. So it works out to minus 1 by 6. So with this we wind up this video. in this we have discussed the covariance of two-dimensional random variable in case of discrete and continuous. We'll meet in the next video.